Morning, everyone.
Good morning.
It's really easy to set. That's good.
How y'all doing?
Hello.
All right. Main plan for today is we're going to conclude chapter 10, and that means we're going to cover the last new thing that I want you to know before the end of the semester, and the last formula I'd like you to be able to use on the exam. I'll go over all of that information in concrete terms. Specifically on Wednesday, we introduced the concept of the Doppler effect, and today we're just going to do the math to make sense of how that works. Additionally, once we conclude that today, we're going to move into exam prep territory. I'll go ahead and let everyone know that on Brightspace, I have updated the final exam tab and almost fully updated the practice task. I actually want to add one more question to it, just a very short concept question. Make sure you know the nature of sound waves. But that is there as a study resource. I'll be uploading the answer key to it this afternoon. And the current answer key that's there is outdated. Note it says 2022. We'll go over the concept list for the exam today before we break. We'll spend Monday making sure everyone feels comfortable for the upcoming exam, address any concept or math questions you guys have for it. And to look quickly at the calendar for the following week. Today is Friday, December 1st. Happy December, everybody. Next Monday is the last day we're going to have for class. If this needs to be said at all, no lab next week. Tuesday the 5th is officially the last day that I can require assignments to be due. So that is the official date that all of the homework is due. If you need an extension to continue studying it, you may ask for one. I may just do that anyway. But that is also therefore the official day that I would ask for the makeup lab to be turned in if you are going to be working on that. Unofficially, I just need it before grades are due on the 15th. But officially, the due date is Tuesday, December 5th. Then, Wednesday is reading day, and then exams start. This course's exam will be offered at 5 different times between Thursday the 7th and Friday the 8th. The 5 different times are currently written on the sideboard over there. I'll also email them out so you have them in writing. Originally, there was just the 3 that the school had scheduled. I have since added 2 more. On Thursday the 7th, the 3 exam time slots are 8:30 a.m., 1:30 p.m., and 5:30 p.m. on that Thursday. On Friday, the 2 slots are 8:30 a.m. and 5:30 p.m. I've added more slots for convenience sake on you guys, and additionally because I will be out of town on Friday, so Dr. Owens will be proctoring the 2 Friday exams on my behalf. So I'm adding more Thursday ones just to give you guys some more flexibility, and so that I'll be in the building longer to answer any questions you guys have before you take it. I'll be in the building on Thursday from likely 8 a.m. to 9 p.m. So if you need anything, find me that day. So you can pick any one of those times. Any questions or concerns from you guys before we continue on today? All right. In that case, let's concludes chapter 10. On Wednesday, the last concept we address is that of the Doppler effect. This is the name for the phenomenon that you've probably noticed when an object rushes past you and the frequency of sound you hear from it changes, whether or not it's moving towards you or away from you. So in that moment it passes you, it suddenly goes from higher pitch to lower pitch in an instant, and you get that meow effect. The knee is high pitched and the meow is low pitched, relatively speaking. This happens because the source of the sound is moving, and if a sound's source is moving, that's going to cause the sound waves to either bunch up closer together if the object is moving towards the waves it just made, or if it's moving away from the waves it just made, that's going to cause the waves to space out. If the waves bunch up together, that drives down wavelength and drives up frequency. If the waves get spaced out, that drives down wavelength, that drives up wavelength and drives down frequency. We're going to show the math for how that works today to make sure that that makes sense, prove how the method works, and this will be the last new formula that I'd ask you to know this semester. As such, there is a practice version of the practice exam. The formula in question for the Doppler effect is this one right here. And the formula reads, F observed, this is the frequency of sound that you, as the observer, would hear, is equal to F source, the original emitted sound frequency that the device or object in question is supposed to be emitting, times wave speed plus your velocity divided by wave speed minus the velocity of whatever is making the wave. We're going to go through how this works, look at each part of it, and work a few examples. What this formula basically does is, most objects only are supposed to emit a specific number of frequencies of sound. Like the siren on an ambulance is going to do the same thing regardless of whether or not it's moving or whether or not you are moving. The object in question is only supposed to emit a specific frequency of sound. So it's going to keep doing whatever it was built to do. It's always going to put out the same frequency. So F source is the original intended frequency that the thing is supposed to be making under normal circumstances. This fraction over here is designed to adjust that frequency based on the velocity difference between you and whatever is making the sound wave. So this fraction takes the original frequency and changes it to create the final frequency that you actually hear. I'm going to show how this works numerically. Any questions before I start throwing some numbers on the board? All right. I've been talking a lot about how this relates to ambulances, so let's use that for our example. The siren on our specific ambulance of today is going to be designed to emit 6,000 hertz sound waves, so that is their frequency. That is the original source frequency, because the ambulance, the siren on the ambulance is what's making this sound. It's designed to output 6,000 hertz, and that's what it's normally going to do if everything was standing still. So that is going to be our source frequency, the original frequency made by the ambulance. And if you and the ambulance are both sitting still, that would be the frequency that you hear. To kind of prove how that works real quick, using this formula, if you and the ambulance are both sitting still, then both of your velocities would be zero, correct? So just to demonstrate real quick, I'm going to tweak this slightly. I'm going to show what would happen if nothing is moving, if everything's velocity is zero. If everything's velocity is zero, your velocity as the observer and the source's velocity would both be zero. And that doesn't end up changing the frequency at all, because this fraction that those velocities are a part of would just simplify down to 1. Speed of sound divided by speed of sound is just 1. So if these are both 0, you're not going to add or subtract anything to the wave's speed at all. So 343 over 343 simplifies to 1. 1 times 6,000 is 6,000. So if nothing is moving, you will hear the normal intended frequency. Does that make sense? Now things start changing once they start moving. So instead of standing still, you are going to stand, well, you are still going to stand still. We are going to plant our feet and remain in place. And the ambulance is now going to drive at a rate of 30 meters per second. We're going to see what that does first as the ambulance moves towards us, and then separately what happens as it's moving away from us. So now instead of both velocities being 0, the ambulance as the source is going to move at 30 meters per second. And since the ambulance is what's making the sound, that means V source is 30, and we as the static observer remain in place, our velocity stays 0. So, the formula says, the observed, what we actually end up hearing, is equal to the original frequency times, and I'll say again, just V is a wave speed, the normal speed the wave is supposed to be moving at. And since this is a sound wave, we're going to plug in the speed of sound in both positions. It's the same V, unless it has a subscript, it's the same V, it's the speed of the wave normally. So 343 is what goes into both of those positions if that is your speed of sound. On the top part of this fraction, we would add our velocity to the speed of sound, but we're not moving. Our feet are planted, we're not going anywhere. So the top part of this fraction doesn't change. That's just going to remain the speed of sound. On the bottom part of the fraction, we take the speed of sound and we subtract the speed of the source. We, the observer, are at 0. The source, the ambulance, is what's moving. So that's where the 30 is going to go. And the question then is, what sign do we put on that 30? Because normally we think of positive and negative as forward positive x or backward negative x. There's a slight alteration to that for how this formula works. For either velocity in this formula, observer or source, you plug it in as positive if it's drawing toward the target, and negative if it's drawing away from the target. If the ambulance is driving towards us, we would input its velocity as positive. But we're inputting it as positive into a position with a negative sign. The formula demands a negative lives there, and we are going to put in a positive number. So that negative that's in the formula will remain. That negative is supposed to be there regardless of what we plug in. So, if the ambulance draws towards us at 30 meters per second, this velocity source is positive 30, and we are going to subtract positive 30 from 343. And this funky looking fraction, based around the relative velocity of source versus observer, is going to take that 6,000 hertz and adjust it per the Doppler effect to tell us what we actually end up hearing. Question so far? All right. Purple marker is running out of ink. Switch to blue. So, the way that this fraction shapes up, the top is just going to remain 343. And the bottom, 343 minus 30, becomes 313. That fraction is now greater than 1. So this is going to drive up the frequency we hear. So our original frequency times 1 point something, something greater than 1, it's going to give us a bigger frequency for our answer. Does anyone run that calculation yet? Okay, I'm not. I get an answer of 6,575 hertz. Do you agree? Note again, that is a bigger answer. The ambulance drawing towards us has driven up the frequency that we hear. This happens because if the object is moving towards us, it's kind of catching up to the sound waves it already made. So the next one comes out closer to the previous one than it's supposed to. If the wavelength is supposed to be 1 meter, if it's supposed to be 1 meter when the ambulance isn't moving, if the wavelength is supposed to be 1 meter, but the source moves closer to the wave it just made, that's going to drive down the wavelength because the next wave's coming out sooner than it's supposed to. Driving down the wavelength drives up frequency, as long as wave speed stays the same. So, when an object draws towards you, you hear a higher pitch than you're supposed to. So that's the higher pitched me part of the meow. And that would, in this particular case, be a difference of 575 hertz. That is a big enough shift for a human ear to be able to detect. You can normally tell a difference of about 500 hertz between sounds. It might be harder to notice if the ambulance speeds up over time, but if the ambulance immediately somehow jumped from 0 to 30, you could hear the sound immediately change. Bless you. If you want to see the difference, or rather hear the difference yourself between 6,000 and 6,575, the makeup lab I sent out has a link to a sound test, which plays every frequency of sound a human can hear. And you can use that test to hear yourself the difference in pitch between the two frequencies, just to prove that they are discernibly different to a human ear. So this is what happens when the object drives towards you. Questions? All right, now we're just going to change it slightly to show what happens if the ambulance is instead driving away from you. This is only going to change one part of the formula. And that's because the speed of sound didn't change, our velocity didn't change. The only thing changing is the sign we put on the ambulance's velocity. If it's still driving at 30 but away from us, we're going to add a negative sign on front of that 30. The number you plug in depends on towards or away. We're going to plug in a negative, and then the formula, since it already had a negative there, is going to end up making it positive. That's on purpose. And that is going to turn this fraction from one that is greater than 1 to one that is smaller than 1. So now the number on the bottom is bigger than the one on the top. This fraction is smaller than 1. And therefore, that is going to drive the perceived frequency down. To approximately 5,517 hertz. So a similar jump down as the other was a jump up. The first time it jumped up 575, here it jumps down about 480 something. So a similar shift. And again, that's a big enough difference from 6,000 for you to be able to perceive it, but the really big difference is between the two calculated frequencies, because they're like almost 1,000 hertz apart, actually slightly more than 1,000 hertz apart now. And that's why you get the really big extreme contrast between the knee and the ow, because the vehicle's only next to you for like a split second. Every second before that, it's drawing closer. Every second after that, it's drawing further away. So at that split second, it suddenly shifts from your perspective from that to that. And that's an even bigger difference, and that's why you can really notice it in that moment it passes you. questions? Feel good? Explain that weird thing you've noticed your whole life. All right. I'll point out a couple things about this particular formula before we end this part of the lecture for the day. First thing I'm going to point out is that this works even if you are moving instead of the source of the sound. It would just change where the numbers end up going. So don't erase anything in your notes. I'm just going to change what's on the board for simplicity's sake because I only have so much space. We're now going to look at a parallel timeline where instead of the ambulance moving towards you, the ambulance is parked and we are going to be the ones moving around. So we are first going to run towards the ambulance at 30 meters per second, and then we're going to run away from the ambulance at 30 meters per second. Maybe you're a superhero bringing people to the ambulance to get help. Maybe you're an ambulance chasing lawyer. The why is up to you. So again, don't erase your notes. I'm just showing what changes. If we were the ones moving, we're still the observer because the ambulance is still making the waves. We're the ones observing them. But what would change here is the ambulance is parked and now we're the ones running. So that's going to change which one of the two numbers is zero. We're just going to switch where we put things. Same formula, but now the source is parked and we're the ones running. If we're originally still running towards the ambulance, we're still going to plug in a positive number. And this is still going to cause the moving closer to the ambulance version to drive up in frequency. Originally, the frequency went up because the bottom of the fraction shrank and the top stayed the same. Here what's going to happen is the top of the fraction grows and the bottom stays the same. Because we're still going to put in positive 30, but there's not a negative sign there to change it. So now the top becomes 373 and the bottom is the normal 743. So the fraction is still bigger than 1. Doesn't matter if we're moving towards it or it's moving towards us, the fraction should still turn out bigger than 1 if the objects are getting closer together, and that's going to drive up the frequency. It won't be exactly the same, but it'll still be higher than 6,000. In particular, instead of 6,575, it would be closer to 25. Not the same, but still higher than the 6,000. The frequency still goes up when the objects get closer together, regardless of which one is doing the moving. In this particular case, rather than the ambulance drawing closer to its own sound waves, you are running into the sound waves so they reach you sooner than they're supposed to. And that still ends up shrinking the wavelength because they are going to hit you sooner than they're meant to. Still drives down wavelength, still drives up frequency. And the inverse is still true if you are running away from the ambulance. If you're running away from the ambulance, we're going to plug negative 30 into the top. The ambulance is still parked, so that'll still say 0. Now it's plus a negative, so subtraction. And so the fraction will become 713 over 743. So the fraction, when moving apart, is still less than 1, and that'll still drive the frequency down. Bless you. Again, not to the exact same number, but still less than 6,000 by a similar margin. And this is because as you move away from the source of the sound, the waves
would hit you further apart than they're meant to, driving up wavelength and down frequency. So you would get this effect not only as the ambulance passes you while you're standing still, you'd get the meow if you are the one running towards and past it. You would just have to be moving at 30 meters per second, which is superhuman. So, congrats. Human walking speed and most human running speeds are too slow for this effect to be very noticeable, because if we plugged in like 3 meters per second instead, the frequency wouldn't jump as much, the fraction wouldn't be as much of a difference. So you only get this effect for larger velocities relative to the speed of the wave. But if you're fast enough, you could hypothetically trigger the Doppler effect yourself if you plant a speaker somewhere on the ground, run towards and past it as fast as you can. You get some degree of meow from that, just not as extreme as if it was the speed of a car. I also find it harder to concentrate on sound if I'm running, but it's still an experiment you can try. So, regardless of which object's moving, if two things are drawing closer together, wave frequency increases. If things are drawing further apart, wave frequency decreases, regardless of which object is doing the moving. Questions, concerns? All right. I would like you to be able to use this formula for the exam. First, just transparency's sake, there will be one question on the exam that references what we've been talking about for sound. It'll have one part of that question will ask you to use this formula in a similarly straightforward way as we've been using it today. It'll give you all the variables save for one, and you solve for the last one. And there is a practice question for it on the practice exam. Before we conclude Chapter 10 officially, I just want to point out a couple other places where this factors into life on planet Earth. I've been talking about the meow effect all day. There's a few other places though. One, any sort of human-built speed detection technology that uses sonar or radar uses this principle. For example, a radar scanner that someone might use if they were measuring the speed of a race car. Because usually they've got someone with one of those speed detection things pointing at the racetrack to see how fast everything's moving without having to actually be down there watching everyone's speedometers. What those devices do is they shoot radio waves at the object, and the machine knows what frequency it's creating. It's designed to emit a certain frequency, so it knows the frequency it's outputting. And what's going to happen is it's going to receive a specific frequency back, because objects do tend to reflect waves that strike them. You guys know what an echo is. That's when sound waves bounce off of things. But most waves have a tendency to bounce off of things as it happens. That's the entire reason the standing wave generator works. The speaker makes a wave here, it travels to the other end, and then it bounces back. So waves love to reflect off of things. How that usually works is the object will absorb the wave and then re-emit it. And this is why sound dampening materials, they just absorb the wave and never let it back out. Now, technically an echo is not the same sound wave, it's a freshly re-emitted one. And what the radar scanner will do is, it emits a certain frequency of radio wave, it'll receive back a different frequency, because when the wave bounces off of the moving object, now that the object is basically the new source, or now that the race car is the new source, that's going to change the frequency based on the race car's velocity. So the radar scanner is going to get back a different frequency than it emitted. And the computer is designed to take those two frequencies and use this formula to figure out the velocity of the object that the radio wave hit. So, all human-built radar, sonar, things like that can tell you how fast something is moving, this is how it does it. It's just programmed to use this formula automatically. also means that those devices are best used when standing still, when V observer is 0. So speed detection is actually less effective if the speed detector is moving, and the speed detectors in police cars tend to be moving. So keep that in mind if you ever get a speeding ticket. Their standards are often not accurate. All human-built radar sonar uses this, and that means that this does work with electromagnetic waves, not just sound waves. But if you were using radar radio waves, it'd be the speed of sound instead of the speed of light. But it works with every type of wave. Other places where this would use like electromagnetic waves is you might have heard like in a movie or a NASA documentary someone talk about red shifting or blue shifting in stars. It's the same effect where if a star is moving towards us, the light it's giving off tends to shift to a higher frequency towards blue. And if it's moving away from us, the light it gives off shifts towards lower frequency, which is red. So NASA scientists use this to figure out if something in space is moving towards or away from us, same way as the radar scanners do. Last thing I'll mention is every echolocating animal does this math in their head. Because not only can a bat scream at things and figure out how far something is away based on how long it takes the wave to come back, they also listen for what frequency comes back. Because the bat knows what frequency it makes, and it listens to see if the frequency coming back is higher or lower. If the frequency it gets back is higher, it means the thing the wave bounced off of is drawing towards it. And if the frequency it gets back is lower, the thing it bounced off of is getting away. And it's able to do this math in its head. Every echolocating animal can do this in their brain faster than thought, or at the speed of thought. So I think that's neat. Animals are smarter than we give them credit for. Questions? All right, that's chapter 10. Again, this is the last formula I would ask you to use, the last new thing I'd ask you to use on the test. Exam. Speaking of the exam, I have written, that's not it. Hello. I have updated on Brightspace the information for said upcoming exam. If you click on the final exam tab itself, like with the 2 previous tests, it lists every single concept that will be present on said upcoming exam. The list is basically just the test 1 list and the test 2 list combined with the noted addition of the stuff we've been talking about this week. So the 3 things related to sound in chapter 10 that I want you to be able to do for the exam, I'm going to go over them in concrete terms. 1, I want you to understand the physical nature of sound waves, meaning I want you to be able to tell me that they are mechanical, longitudinal waves. Mechanical meaning that sound requires a physical medium. You can't hear in space, but you can technically hear underwater, because air and water are mediums that the sound can travel through. Sound is mechanical, and sound is longitudinal. Longitudinal meaning that sound doesn't look like this, it looks like this. It vibrates in the same axis as travel. It is a pulse forward and backward in the same direction it's moving in. Sound is mechanical, longitudinal, and I want you to remember that. This is in contrast to light, which is electromagnetic transverse, basically the exact opposite kind of wave. So, what type of wave is sound? Longitudinal and mechanical. Thank you all for humoring me with that. Second thing I'd like you to be able to do with sound is wave speed equals frequency times wavelength. Similarly, wave speed can also still equal displacement over time. But note again, this is the relationship between wavelength and frequency. If I say, tell you a sound wave is 30 hertz, I'd like you to be able to tell me what its wavelength is, for example, based on its velocity. And lastly, Doppler effect, the formula we were using today. There is, again, just to give you guys as much accurate information as I can, the exam is finished, the document is finalized. It is 16 questions, so slightly shorter than test 1 and 2 fused together. Of those 16 questions, 5 are concept short answer sort of thing. One of them is still Newton's laws. You have to be able to identify them like you did on test 1. 5 concept short answer, including that one. That means 11 math questions. One of those 11 math questions is about sound. And I would like you to be able to use these 2 formulas as it relates to it. These 2 formulas do show up on a practice exam. Speaking of the practice exam, I have mostly updated this. I actually want to add one more small thing. Again, make sure you know sound is mechanical, longitudinal. So this will end up being, the practice exam will end up being 23 questions in comparison to the exam's 16. I always make the practice documents longer and more difficult so that you make mistakes here and not there. So when you load this up and you see 23 questions, do not panic. I have written the exam with the time limits in mind. There's only 16 questions and I've designed them to go quickly. Sound fair? All right. Now my aim for any remaining part of today and also for Monday is to make sure you guys feel comfortable for the exam, going over the list of concepts, going over the practice exam, helping you guys with homeworks, quizzes, and anything possibly that could be on your minds. And I think you guys are going to do great. Anything on your minds right now? All right. Make sure to bring any questions you have to class on Monday. Even if you don't have any questions, I'll have something cool to show you. I didn't have time to set it up for today, so I'll show it to you on Monday. So show up. There'll be something cool, I promise. And bring any questions you have. I want to make sure you're feeling comfortable before the last day of class ends. Never do anything. If you have questions about anything, practice exam, homework, or whatever. And